Welcome back to ECE 320A. Homework number 3 is due today. You have until midnight, not quite midnight, 11:59 to submit that on mastering. And just as a preface for getting into homework number 4 and 5 when we're doing inverse Laplace transforms, if you're interested in exercising your calculator, if you own an 89, a TI 89 or a TI Inspire, if you want to know how can I use that to find these inverse Laplace transforms or these partial fraction expansion coefficients, even when I'm doing complex poles, there's some videos that you might want to watch. They're not that long, 6 or 9 minutes, I think, for real and complex. The links are available on our website in D2L. What I want to do today is go over ladder analysis via using a circuit or performing circuit analysis using ladder analysis techniques. Have you heard of that before this class, or have you performed ladder analysis before ECE 320? You've heard of it? Okay, so we'll try to make it clear. Actually, I'm going to move through it very quickly today, but I would encourage you to maybe go home and try to reproduce what I talked about today. You'll have it in the notes and the video to sort of check your work, but ladder analysis actually allows you a way to sort of check your work as you're solving the problem. In KVL and KCL analysis, nodal analysis and mesh analysis, you're sort of putting all of these equations together and then doing an inverse, and you just hope that the answer is correct. Ladder analysis allows you to sort of intuitively have a feel for what's happening as you progress through your solution from beginning to end. That's the idea behind ladder analysis. And then we'll get into getting back into the kitchen, if we were in the living room, from the frequency domain. If we've now done all of this analysis in the frequency domain, how do we get back into the time domain? And that's what inverse Laplace transforms allow us to do. You can perform ladder analysis in the time domain, writing differential equations or integral differential equations, or you can transform your circuit variables and work in the frequency domain with these complex variables S to perform the ladder analysis. It works in either domain. And the reason for the name ladder analysis is because the circuit looks like a ladder if you laid it on one of its edges, meaning the different meshes sort of look like the rungs in a ladder. That's where I think the ladder analysis name comes from, and that's how I'm using it. And as I said earlier when I was discussing the goals for today, the ladder analysis actually allows you to sort of feel or see the solution develop in front of you without having to just sort of, oh, I hope I did the math correct. Here's the current in this particular mesh, or here's the voltage at this particular location. Here, we're going to actually derive the governing differential equation relating an output voltage to the input voltage source in sort of a progressive way. We'll evolve from beginning to end. And we'll do that by starting with the output equation and working our way back up the ladder or down the ladder towards the source. We'll try to sort of walk our way through these rungs of the ladder doing essentially KVL and KCL at each step effectively. And it really is probably easier to think about using an example. And like I said, these notes will be available to you. I'm going to probably scroll through this quicker than you can write everything down, and I would maybe encourage you to watch this like a movie and then try to do it at home later and say, I'm stuck. How did he go from this step to that step? What we're wanting to do is we're wanting to find a differential equation that contains the voltage across that capacitor and this source V of t. We want to try to find an equation that describes the dynamic behavior of this electric circuit. If that's our goal, what would you expect to maybe see at the end? How big of a differential equation? By that I mean, what's the order of the differential equation you would be anticipating seeing arising from this circuit? And I've colored it a lot of different ways, but hopefully you can maybe, based on what we've talked about so far this semester, suggest or have a clue as to what the order of that differential equation will be. Second order. We have two energy storage devices. We have three resistors, but those don't really matter in terms of the dynamical behavior. I mean, they will shape it, but our energy storage devices in the form of a capacitor and an inductor allow us to say, oh, after we've done this analysis, I would expect to see a second order differential equation. You're expecting then a V sub c double prime plus something weighting a V sub c prime plus something weighting a V sub c equaling maybe something scaling the input V of t. That's the differential equation you're anticipating ending up with. And let's now try to walk through that. I've labeled, if you can see what I've done, I've labeled a lot of the voltages, I've labeled a lot of the currents, and it looks like I didn't label the voltage here that I didn't label this voltage because it's the same as V sub c. So if I refer to V sub r sub 1, that's really just V sub c. And what I want to do now is start working my way back, starting with V sub c. Then I want to find an equation for I sub c in terms of V sub c. Then maybe I want to find an equation for I sub r sub 1 in terms of V sub c. Then I sub r sub 2 in terms of V sub c and its derivatives. And I hope you can see that I'm working my way from the right, the top of the ladder, back to the bottom, which now incorporates or involves the voltage source. That's what I'm trying to do with this ladder analysis. And that's what I'm stating here as the goal. I'm trying to find a differential equation relating the output voltage, which is the voltage across that capacitor, to the input voltage source, V of t. And I'll try to see if I can come up with some linear combination of V sub c, V sub c prime, V sub c double prime. And you said that's probably what you'll end up with, is a second order differential equation. You won't be seeing a V sub c triple prime. If you do, then you might say, ooh, did I make a mistake? Where is my error? And we're going to rely a lot on Eli and ice. So here's step one. We want to now describe or rewrite these different variables in our circuit in terms of V sub c and its derivatives. And I sub c, if we scroll back to the circuit, that's simply the current through that capacitor is just coming to us from ice. I sub c is equal to c V sub c prime. And there's now an expression for I sub c. What's I sub r sub 1? I would say that's Ohm's law, isn't it? We know the voltage across that resistor, R sub 1. We just divide by that resistor. That's Ohm's law, and we now have an equation for I sub R sub 1 in terms of V sub c. If we now know I sub R sub 1 and I sub c, applying KCL at node A allows us to write an equation for I sub R sub 2. Once we know I sub r sub 2, we can find v sub r sub 2. That's Ohm's law again. R sub 2 times I sub r sub 2. A lot of subs, r's. Once we have I sub r sub 2, then what do we do? Well, maybe we have v sub r sub 2 and we have v sub c. Do you see that we can now find v sub r sub 3 using KVL? Once we have v sub r sub 3, we can get I sub r sub 3 by Ohm's law. Now apply KCL and we can get I sub L. Once we have I sub L, we can use Eli to get v sub L. V sub L is L di sub L dt. And we have I sub L in terms of v sub c and its derivatives. And we're almost done. We can just write one more KVL minus v plus v sub L plus v sub r sub 3, and we're done. Now we have a way of relating v to v sub c and its derivatives. Do you see how we walked through that ladder, or walked down the ladder? If this is the bottom, the voltage source, that's what our steps are going to be. Step 1 was ice. Step 2 was Ohm's law. There's I sub r sub 1. And we just keep working our way back towards the source. Step 3 is KCL at node A. Once we have I sub r sub 2, and now we've written it in terms of v sub c and its derivatives, we can find in step 4, using Ohm's law, v sub r sub 2. So we scale the previous current equation by r sub 2 through Ohm's law, and now we have v sub r sub 2 in terms of v sub c and its derivative. Step 5, KVL to find v sub r sub 3. Again, v sub r sub 3 is a combination of v sub c, a linear combination of v sub c and its derivative. Once we have v sub r sub 3, Ohm's law allows us to obtain I sub r sub 3 by dividing by r sub 3. Step 7, KCL at B allows us to find I sub L. Like I said, you may not be able to stay up with me if you're writing all of this down, but you can do this at home tonight. Try to reproduce what I've done today. There's I sub L. Now it's involved, but all it contains are variables v sub c prime, and v sub c. That's it for now, isn't it? It's going to be v sub c double prime once we use Eli in step 8 to write or solve for v sub L, the voltage dropped across that inductor. That's L times the derivative of that equation right there for I sub L of t. Step 9, that ladder was kind of long, wasn't it? Are you as tired as I am after going through 9 steps of a 3-rung ladder? Yeah, we need our exercise. So this is now, v of t is now written in terms of v sub c prime, and v sub c double prime. And all of that came out without sort of putting it into a matrix or some kind of messy coupled set of equations and trying to do inverses. It all happened kind of gradually and smoothly in this progression of steps from the output equation down to the input. And we now have a feel for where those individual pieces of that equation come from. And a maybe more intuitive idea that, oh, I kind of believe this equation. Whereas if you put it all into a matrix and do the inverse, you go, well, I don't know, Has all these relationships, but I'm not sure if that's correct. This one you can trace your work back through. And what I'm going to do, I'm getting lazy. I'm going to replace all of these coefficients. Do you see that the coefficient beta 1 involves quite a few terms? Beta 2 involves quite a little bit less, but it's still kind of a mess. Beta sub 0 isn't too messy. It's 1 plus r sub 2 over r sub 1. But now I can say, oh, here's my second order differential equation that relates the applied voltage, V of t, to the time rate of change of that capacitor voltage through this second order differential equation. What if I now wanted to Laplace transform that? Now we have to Laplace transform derivatives and variables v sub c. The first one, or the rightmost one, is easy. That's just the Laplace transform of little v sub c of t. That simply becomes b sub 0 or beta sub 0 capital V sub c of s. The others involve initial conditions if those are non-zero. We have the Laplace transform of a first derivative, and then we have even more initial conditions, not only the initial condition on the voltage of that capacitor at time 0 minus, but also its rate of change at time 0. How is it sloping at time 0? Well, that's now an initial condition that we have to have if they're non-zero in order to find or solve for V sub c. We're assuming that somebody is going to tell us what the applied voltage is. What that applied voltage is, little v of t, we can now Laplace transform, and that will give us capital V of s. What we don't know is what little v sub c of t is, the voltage across that capacitor in the time domain. But now we have an expression involving that little v sub c of t's Laplace transform. We have capital V sub c of s. Can we solve for it? Now we just factor all of these pieces, and we end up with really sort of two sets of terms. We have a beta 2 s squared, a beta 1 s, and a beta sub 0, all scaling V sub c of s. And you would expect that if we had a second order differential equation. You would expect to maybe have a second order polynomial in s. And that's now weighting this yet to be determined Laplace transformed quantity for the output voltage V sub c of t. And then we have initial condition terms. If we're trying to find V sub c of s, well, it's going to involve this polynomial, this second order polynomial, and we'll call that our characteristic polynomial, which if we set it equal to 0 is now our characteristic equation. And why do we call it characteristic? Because it gives us the character of that circuit. And I do this because it governs that the roots of the characteristic equation give us the poles or the modes of how this system naturally wants to move. That's what we have when we now find the roots of this characteristic equation. How does it naturally want to shake? If you initialized this capacitor and inductor with initial conditions and you didn't even have an input applied, this system would want to move in some way. And how it moves obviously depends on the values of beta sub 2, beta 1, and beta sub 0, and what were involved with those. R's, L's, and C's. So depending on how you've picked from the stockroom window, I'll take a R1, of this amount. I'll take an R2 of this amount, and I'll take an R3 of this, and I want a capacitor and an inductor with these values. For what reason? Maybe to produce a particular circuit behavior. That's what you would do in a circuit design. But now if we solve this equation in blue for V sub c of s, do you see all we really need to do is divide everything by that characteristic polynomial? All terms. And we have one term that's capital V of s, our applied voltage as Laplace transform, divided by that characteristic polynomial, and these initial condition terms divided by the characteristic polynomial, which I'm just calling d of s. And now we're probably going back to a differential equations type class, a forced response. Well, maybe you didn't talk too much about initial conditions and forced responses in diffie-q, but that's how you can think of this capacitor, its voltage. If you had no initial conditions, if it was unenergized, you would just have the capacitor influenced by its natural modes. You're dividing by d of s, and how you're exciting it with capital V of s. If, in fact, you didn't excite it, didn't have a voltage source applied, it would now naturally move based on this set of initial conditions on your capacitor and the way the system naturally wants to behave given by your characteristic equations roots. And those could be real, they could be complex. The roots of a quadratic. And you should be able to use the quadratic formula to find those roots. In this RLC circuit, what would you expect? How would you expect this system to naturally shake? If you energized the capacitor voltage and the inductor current, didn't apply an external voltage source, you then said, okay, go. From those initial conditions, what would you expect to see? Can you even comment on that based on just this circuit? What would you expect to see on the trace of an oscilloscope if you were watching that, let's say, that capacitor's voltage? If I completely just get me to spring break, I don't care. What am I trying to coax out of you? What would you expect out of a circuit like that? It's going to depend on the R, L, and C's, right? But naturally, what's going to happen? You've got resistors. What are they doing? They're removing energy from that circuit. So you would expect, if this is even complex roots, maybe they'll shake a little bit with some sinusoidal behavior, but they're going to exponentially collapse. If they were too real, then they would both collapse. What I was expecting you to say was, well, it's a passive circuit. It should just exponentially decay the response or that voltage. How it exponentially decays obviously is influenced by the inductor, capacitor, and those resistors. But generically, you could say, oh, it's going to be an exponentially decaying response. If we wanted to go back into the time domain, then we need to inverse Laplace transform these two pieces of our solution for capital V sub c of s. And 1 is due to the forcing function, capital V of S, the applied voltage. That will be our forced response. The other piece of that response will be due to the initial conditions. And you could now think of that capacitor's voltage being a combination of a forced response and an initial condition response. If that's the case, if it's now in red, that must be important. You see that. Now we need to learn how to do that. How do we inverse Laplace transform? And the strategy is essentially find these expressions in the table and go from the frequency domain, the kitchen, back into the living room, the time domain. Generically, if we're given a capital F of S, before in that example we were given a capital V sub C of S, some expression. We now want to take that back into the time domain. And we want to do that by manipulating capital F of S into terms that look like terms in the column, in the frequency domain column in our table. And then we can say, oh, this is what it looks like in the time domain, and write down almost immediately the structure of our answer or solution. And that's what I'm meaning by little f of t is now equal to the inverse Laplace transform, this script L inverse of this transform expression, capital F of S. So let's do that. Here's an example. Suppose now you're given, after all of this analysis, that capital V sub C of S is 4s plus 1 in the numerator all over, and on an exam or on a homework you may be given the denominator as you're working in an unfactored form. It might be a quadratic. It might be a fifth order polynomial. You now need to factor that. And once we've factored it, now what we want to do is expand this. Whoa, let's not do it in red. That'll make everybody nervous. So now what we want to do is rewrite this in a partial fraction expansion. We're using each of these factors in the denominator as individual terms or pieces on the right-hand side. We're saying, oh, we want some amount of a term associated with the s plus 1 factor, and we want some amount given by b, associated with the factor associated with this s plus 2, and this right-hand side is what we will call our partial fraction expansion. And just knowing that we can write this as a combination of two terms, we can immediately write down the structure of our time domain answer, because we know what gives rise to a denominator that looks like s plus 1 in the time domain. The root that satisfies s plus 1 equal to 0 is what value of s causes that factor to disappear or vanish or to become equal to 0. What value of s causes s plus 1 to equal 0? S equal to minus 1. So that s equal to minus 1 is one of our modes, actually one of the roots of our system that gives rise to a mode, and that mode that it gives rise to is e to the minus t, and maybe I should make it explicit, e to the minus 1 t, where this minus 1 is coming from the root that satisfies s plus 1 equal to 0. And it will be weighted by a. This is now going to give rise to the first part of our time domain expression for little v sub c of t. We know that if we Laplace transformed e to the minus t, we would end up with this something over s plus 1. The same goes for the second term. What's the mode associated with the second piece? E to the minus 2t, where this minus 2 is coming from that second factor. And what we want to do now is determine what the a and the b are equal to. So we need to find a and b in, let's say, star, where now this is equation star. And whatever is on the right-hand side, that needs to equal that blue transform expression on the left. So whatever a is and b end up being, when we combine them, they better give us in the numerator 4s plus 1. That's one way of thinking of it. But we can actually solve for a and b independently because they're distinct roots. Minus 1 is distinct from minus 2. And because of that, we can use what's called the Heaviside cover-up method. Or if we come back here and we said, oh, I want to solve for a, I can't illustrate this in the video, but I can do it in class. I can cover up this s plus 1 factor and then evaluate what's remaining at the value of s that would cause that s plus 1 factor to equal 0. Or I just replace s everywhere with minus 1. That's what's meant by the cover-up method to find a. I multiply everything in this expression by s plus 1 and then let s equal to minus 1. Or a now becomes a is equal to s plus 1 times v sub c of s. That's really what I'm doing, evaluated at the value of s that causes that s plus 1 to vanish. But multiplying capital V sub c of s by s plus 1 really cancels that factor in the denominator of s plus 1. I'll do that explicitly here. Meaning those two cancel. We don't need to worry about that. And now we evaluate what's left at the value of s equal to minus 1. Or this now says that we have 4s plus 1 over s plus 2. That's what we get when we cover up that one factor. We evaluate it at minus 1, and we now have 4 times minus 1 plus 1 over minus 1 plus 2. Or this is now minus 4 plus 1, or minus 3, over minus 1 plus 2, which is 1. A is now minus 3. That's how much of that mode, e to the minus t, we have making up v sub c of t. And we can find b in a similar manner. B is now going to be s plus 2 times v sub c of s. Now we replace s with the value of s that causes the factor underneath b to vanish. And that was s is equal to minus 2. Or this is now s plus 2. I'm doing this longhand. I won't do this again probably, but I'm trying to illustrate where all of these pieces are coming from so that it's clear. Or we can now say, oh, b is in fact 4s plus 1, which is what we would have obtained if we covered up that s plus 2 factor in the denominator. And now we replace s everywhere with minus 2. We now have minus 7 over minus 1, or b is now 7. Once we found a and b, we now know that capital V sub c of s was a, which is minus 3 over s plus 1, plus 7 over s plus 2. And in fact, if you simply did expand on your calculator, well, it depends on the calculator, an Inspire or an 89, if you put in that argument, this expression that we started with, 4s plus 1 in the numerator over s squared plus 3s plus 2, you'll actually obtain this answer. Boom, in one keystroke. There's the answer in the back of the book. Once we have this, now we know what it looks like in the time domain. We simply have an e to the minus t mode scaled by minus 3. And we have an e to the minus 2t mode scaled by 7. And that's true for time not equal to 0, or non-negative, t greater than or equal to 0. Questions on that first inverse Laplace transform? What if we try another one? Since I didn't see anybody even blinking an eye on that request for questions. So example 2. Suppose we now say capital F of s is 3s over s squared plus 4s plus 13. And now what do we do, or if you're now trying to inverse Laplace transform, sort of what's your focus? What will you be doing when you're confronted or given some transform expression? What's sort of your first thought? Look at the denominator. See what it produces, right? What values of s cause that denominator to vanish? And those are going to be giving rise to our natural modes, or the modes of that inverse Laplace transform. We want to then key in on the denominator polynomial. And maybe it's just instinctive that you see that denominator can actually be rewritten as s plus 2 squared plus 3 squared. Did that just pop out at you? That's the first thing you saw, wasn't it? So where in the world did that come from? Well, if you plug this into the complex or the quadratic formula, you would find complex roots. But now I've written these complex roots in a quadratic way that actually makes it very clear, once you've seen it, that the roots of s squared plus 4s plus 13 are actually s equal to minus 2 plus and minus j3. First, let's see where this factored form comes from. If I gave you s plus x and I said square it, you could do that. This is now s squared plus 2xs plus x squared. And what I'm doing is I'm saying, oh, I know my coefficient that weights the s, the linear power of s, is going to be 2 times something. So in my s squared, if they're quadratic. So here I say, oh, 4 is equal to 2x, and that's going to give me my x in this s plus x quantity squared. Meaning, now I have that this, in our example, corresponded to 4, or that now tells me that x is equal to 2. If that's the case, now I can say, well, my denominator is made up of s plus 2 squared plus something. And in fact, this first piece is s squared plus 4s plus 4. And what do I add to 4 to get my actual coefficient, constant coefficient? That was 13. So 13 minus 4 is 9. This is now plus 9, and 9 I can rewrite as a perfect square of 3. And that's now where this s plus 2 quantity squared plus 3 squared came from. So this is now the s plus 2 squared plus 3 squared, which is a way, if you said, oh, what are the roots of the denominator, that polynomial? They're going to be at minus 2 plus and minus j 3, where this 2 is right there and the 3 is right there. Or what I would encourage you to do tonight is, in this denominator, replace s with minus 2 plus j3 and see if it equals 0, and then replace it with minus 2 minus j3 to verify that, in fact, those two roots, minus 2 plus and minus j3, are the two roots, s sub 1 and s sub 2, that satisfy or make that quadratic vanish. So I'm really saying that s1 I could say is minus 2 plus j3, and s sub 2 is minus 2 minus j3. Once I know that I have complex roots, I can in fact write down the structure of what I expect the time domain expression associated with capital F of s to equal. I expect the solution, little f of t, to be some amount of an exponentially damped cosine and an exponentially damped sine. How much are they exponentially damped? Well, that exponential damping is determined by the real part of those two roots, the minus 2. I now have an alpha e to the minus 2t, and what's the way that it's oscillating? What's the frequency of oscillation? That's the imaginary component of those complex roots. It's oscillating at 3 radians per second. So I now have this is cosine of 3t plus an exponentially damped sine at the same frequency, and the damping is the same. And that's true for t greater than or equal to 0. To relate this to what we talked about last time, where is infinity? Pretty far? Or here's another way of asking that. What's the time constant of this expression? So I've heard a couple of answers. I heard 5 tau. 5 tau is not the time constant. 5 tau is infinity, right? That's the 1% settling time, and tau in the 5 tau is our time constant. And what is the time constant associated with this little f of t? Can you tell me? So in this e to the minus 2t cosine of 3t, can you draw that mentally in your head? Not really? So you need to by the time the final rolls around, or the second exam. What's happening with the sinusoidal piece? The imaginary component gives us the oscillating frequency. It's oscillating at what? 3 radians per second. That's how it's shaking. So if you looked at this curve and you found between peak and peak, the period would be such that 2 pi over that period would equal 3. That's how it's oscillating. How is it exponentially decaying? Determined by e to the minus 2t. So that's how quickly it collapses, is e to the minus 2t. And as it's collapsing, it's shaking, and it's shaking at 3t, cosine of 3t, sine of 3t. Mentally, what you should see then is this exponentially damped cosine and sine. That's what I'm expecting you to see, and how quickly it's decaying is determined by the exponent that weights the cosine and the sine. Or we're looking to see, well, when does 2t, when t is equal to tau, equal 1? And that's how I can now find my time constant, tau, which will now help me figure out what is 5 tau, or what's my settling time, what's infinity, in quotes. What's tau? 1/2. Now the settling time, t sub s, is 5 tau. That's 5 times 1/2, so it only takes 2.5 seconds to get to infinity. To infinity and beyond, and that's only 2.5 seconds. So when is infinity not very big? In our circuits class. When tau is 1/2, or tau is 1/3, and that's really big for electrical terms. It may be in the milliseconds, typically, a tau. All right, well, those were all sort of side notes, but we at least know the structure of our answer. You can visually see what you expect the f of t to look like as a function of time. These exponentially damped sines and cosines, a combination of that. Let's now compute the alphas and the betas. We had an f of s equaling 3s over s plus 2 squared plus 3 squared. One approach for finding this, and I'll call this the common denominator approach, is to do the following. Suppose we now say that we have 3s over s plus 2 squared plus 3 squared. But we know that we expect an exponentially damped cosine and an exponentially damped sine. If you now go into the table of Laplace transform and say, oh, what's the structure in the frequency domain of an exponentially damped cosine? Cosine is going to be s plus 2 over s plus 2 squared plus 3 squared. That's the cosine, exponentially damped cosine. And that we want to weight with a weighting of alpha. In the table, you would find that structure. This structure corresponds to e to the minus 2t cosine of 3t in the time domain. What's the sine structure? Has exactly the same denominator. what does it have in the numerator? Does it have an s plus 2? Does it have a 3 squared? It actually just has 3, doesn't it? It just has omega. It doesn't have omega squared. It's just omega. It looks like 3. That's the omega, and we want to weight that by beta. Now what we want to do is we want to select alpha and beta such that it gives us 3s. There's one equation. How many unknowns do we have? This isn't looking right. We have 2 unknowns, alpha and beta, and we have one equation. We have the numerator that we're equating. But that numerator is a first-order polynomial in S. So we have a linear term in S. What's scaling S? And we have a constant term, which is not even there explicitly, but we have a plus 0 on the left-hand side. And we can equate coefficients of S. We have a coefficient for S to the 1, that's 3. And we have a coefficient of S to the 0, that's the constant coefficient, and that's 0. So we have 2 equations in 2 unknowns. We can now solve for alpha and beta. What I'm trying to say is let's now equate the coefficients in the numerator. In fact, can I, well, here we have alpha s plus 2 alpha, and over here we have 3 beta. And all of those combine to produce 3s. What I'm saying by equating coefficients, let's equate the coefficients associated with s to the first power. On the left-hand side, what do we have that scales s? 3. So we have 3 equaling whatever is on the right. Would you guys wake me up? I'm just seeing if you're awake. I think I lost you about 30 minutes ago. Where's the ladder? We're scaling heights now. You have to get on that ladder and go. We're now doing inverse Laplace transforms, so we've switched topics. But now we have alpha s plus 2 alpha. Is that right? Is that what happens when we distribute alpha across s plus 2? Now I want to say, okay, what on the right-hand side is my coefficient that's scaling s? And it should involve alpha and beta. What scales s on the right-hand side? Just alpha. So boom, I immediately have my alpha. I could end up with 2 equations in 2 unknowns. Here, the first one actually is decoupled. I've now solved for alpha. Alpha is 3. How do I find beta? Well, I find the coefficients associated with everything that's scaling plus something s to the 0. Here was s to the 1. Here is s to the 0. And on the left, what is that? Nothing. It's 0. What's on the right? What are my constant terms? That's what I'm setting equal to 0, correct? S to the 0 is my constant term. That's my constant coefficient. That's 0 on the left. On the right, it's 2 alpha plus 3 beta. And I already know what alpha is. It's 3. So that now I can say, oh, this is 2 times 3 plus 3 times beta. And that has to equal 0. I can divide a 3 out, and I now see that beta must be minus 2 to make that true. Beta is now minus 2. What do I now have? Well, now I have a partial fraction expansion structure for capital F of S, which is associated with complex roots in the denominator. I have a alpha, a 3 times S plus 2 over S plus 2 squared plus 3 squared plus a minus 2 times the 3 over S plus 2 squared plus 3 squared. And now I can immediately write down the answer in the time domain. I can immediately go into the kitchen. That's what I now have in the living room. Now I can go into the time domain and I can say, oh, f of t. And now you need to show me where all of these pieces are coming from, but I'm going to write them down. I'm saying I have 3 e to the minus 2t cosine of 3t minus 2 e to the minus 2t sine of 3t for t greater than or equal to 0. Or if we wanted to, I could write that with a switch. I could say, oh, and I'll even write it differently. It's e to the minus 2t. That's common to both pieces. Let me factor that out in common. That's my exponential decay. And then I have 3 cosine of 3t minus 2 sine of 3t. And I'm going to turn that on for times that are non-negative. So I'll just switch it on by multiplying that exponentially damped cosine and sine with the unit step. Now, where did all of these pieces in my f of t equation come from relative to capital F of S? Where did the 3 scaling e to the minus 2t cosine of 3t come from? I've got a lot of 3s. 3s are wild here, aren't they? Which 3 is the actual 3 that I'm after? There's where the 3 came from. Where did the minus 2 come from? That's there, right? Where did the 3 in the argument of the cosine come from? Right there. That's this 3. Can we do the same thing for the other half of f of t? The minus 2, the 2, the 3. See how you can now quickly write down from this capital F of S expression its time domain version. That's the inverse Laplace transform. Do we have questions? Yes?
Where's the UT coming from?
Where is u of t coming from? Why is all of this now weighted by u of t? And what is that u of t? I should clarify that u of t is the unit step. This is now the unit step. Up. Ladder. I'm sleeping now. This is now the unit step. And what's the unit step actually doing? If we now had this exponentially decaying, let me just draw the cosine because that's easier to draw, but I have something like this, right? How it decays is e to the minus 2t. This 3t is determined by t, so that omega is 3 is equal to 2 pi over t. So if you found capital T, you could plug it or divide it into 2 pi and get the 3. I didn't answer your question, did I? If you're still following. I don't know. He said unit step. What? Well, if this was still, I can't draw it, but do you see what would happen if I covered up that unit step? It would still be playing back here for negative values of time if I didn't have that u of t scaling this expression. I could plug in a minus 1 and generate, so if this wasn't there, do you see I could evaluate this at some minus 1, minus 2, minus 3, and it would just be going bigger and bigger back behind t equal to 0. By putting this magic little unit step right there, what I'm doing is I'm now turning on, this is now the unit step. The unit step is 1, and in fact, well, my drawing is not to scale, is it? Where's this point right there supposed to be if this is the cosine term? If this is just the cosine piece, that would be 3, right? It's 3 e to the minus 2t cosine of 3t is where I start. That's irrelevant to this answer, by the way. But here's the unit step, and do you see that if I have it active, if it's there, or if it multiplies 3 e to the minus 2t cosine of 3t, do you see that I only see this non-negative time portion of e to the minus 2t 3 cosine of 3t? If that u of t was not there, I would have to continue drawing this blue exponential cosine to the left of the origin, to the left of t equals 0. It's really just a fancy way or a compact way of rewriting comma t greater than or equal to 0. These two expressions for f of t are equivalent. And I want you to get comfortable seeing them or playing with either version. You need to say, oh, f of t is valid for t greater than or equal to 0. Oh, I can rewrite that by just weighting it by this unit step, u of t. Yes?
So if you were to say t is greater than or equal to -1, ut plus 1?
So now if I wanted to turn this waveform on or activate it for all time t greater than or equal to -1, that was the question, I think, paraphrased, what would this be? Why am I doing this? What would be here? If I wanted this to be true for t greater than or equal to t equal to -1. I'm really saying, when is my argument non-negative in the u of t expression? I would say, oh, let me see when t plus 1, that's the argument, is greater than or equal to 0. That's true when t is greater than or equal to -1. And that would turn it on for negative values of t from -1 up to 0 and beyond. I've answered that question, so now I'm going to reset this to be what I hope it was supposed to be. Did that answer your question on what would that look like if we really wanted this exponentially damped sine and cosine to actually exist from -1 all the way up to infinity? But how long do you really have to draw this curve? How big is your time axis? If you were plotting this in MATLAB, how long would you make t? Let's see, infinity, sir. Probably bigger than 2.5, right? Maybe 3 would be your limit on t. So you'd go 0 to 3 for the time interval that you're plotting this. I'm going to move on. But you should get comfortable with that unit step having it as a switch. That's all it's being used as. Let's now talk about in general what we're going to be confronted with for inverse Laplace transforms. And I'm going to say that it's as simple as having one of two cases. And all of these cases, which there's just 2 of them, so all just means 1 and 2, all of these cases pertain to the denominator polynomial. And I'm going to say then that all of these roots, for now in this discussion, I'm going to call p sub i's. And these roots of your denominator polynomial that I'm calling p sub I can be real or complex. And here are the 2 cases. 1, we have distinct, or maybe somebody might refer to that as simple, roots. And these simple roots or distinct roots can be real or complex. What does that mean? Well, pictorially, I think you're all comfortable with tents if you've been on the mall. So now we have seen tents all over the place. Maybe they're not circus tents, but you get the idea. Now, if somebody sees you in one of those tents and you're walking underneath it, and they're going, what in the world? Oh, he's an ECE major. He's looking at the frequency response behavior underneath that tent. Right? You're going, oh, there's a pole. Yeah, there's a 0. Now you have this frequency response. You can see it plain as day. So now, that's what we have this S-plane. It's a complex plane, and we could have poles at many different places. But in the first case, we're saying that these poles are basically, you don't have any of these poles on top of each other. They're distinct. They're simple. So if this one was at -1, this one at -4, this one at -2, let's just say it's plus and minus j2. Actually, let's quit with all the 2's. Let's give it a little bit more spice, oscillation. Let's say this is now j3, and this is now minus j3. They have to occur in conjugate pairs. Okay? So there are where our poles are laid out. And now this corresponds to, let's say, an n sub 1 of s over an s minus p1, an s minus p sub 2, an s minus p sub 3, and an s minus p sub 4. Where this is, let's say, p1, this is p sub 2, p sub 3, and p sub 4. Where we are assuming, if we're in case 1, that these real and or complex numbers are not the same. They're not equal to each other. And in particular, you could say, well, if this is P1, we have S minus P1 equal to 0. S is equal to P1 is, what is P1? Minus 1. What's S equal to P sub 2? It's complex, isn't it? It has a real part. It's minus 2 into the complex plane. And how big is it in the imaginary component? It's up 3. P2 is now minus 2 plus J3. This gives rise to a factor of S plus 1. Right? If we would add 1 to both sides, we would have S plus 1 equaling 0. What about this guy? That's the factor it corresponds to. What about P sub 3? It's still minus 2, but it's now at minus J3, and it corresponds to this S plus 2 plus J3 factor. And the P4, so if we wrote it differently in terms of the particular distinct or simple poles that we have illustrated in this circus tent complex plane floor, we would write it as n sub 1 of S over S plus 1, S plus 2 minus J3, S plus 2 plus J3, and S plus 4. And I know you want to just go home and play with this, but I want to play with it now. So here is another way of convincing yourself of what we'd seen before. If I now multiply this out, do you see that I have an S plus 2 squared? The cross terms cancel because one gets scaled by J3, the other gets scaled by minus J3. And what else do we have? We have a minus J squared times 3 squared. But we're electrical and computer engineers, so we know what J squared is. J's the square root of minus 1, correct? What's J squared? Minus 1. So minus J squared is plus. Here is where we come back to what we just talked about earlier. So if you wanted to write that quadratic that has complex roots, you could write it in this form. And now it's in real coefficients, but you've explicitly identified that its roots are at minus 2 plus and minus J3. Another way of convincing yourself of this formula is consistent with those distinct roots. That's case 1. Case 2 is if we actually had repeated roots. And those repeated roots could be real or complex. Meaning, now we might have an n sub 2 of S over an S minus P, let's say to the little n, where now we have n roots at S equal to P. Or, I know you want to play in the tent, so we have to do a complex plane. Here's the S plane. Here's minus 2, and suppose that we now have And I don't show them overlapping. In fact, they're all three right on top of each other, but you wouldn't see that if I drew them where they actually are, so I sort of stagger them. But now, in this picture, I'm trying to illustrate that we have three roots at s equal to minus 2. And that would be case number 2, where we have repeated roots. When we're doing inverse Laplace transforms, where do we focus our attention? On the denominator. We factor that denominator and we say, are all of these roots distinct? If they are, we have case 1. If some of them are repeated, we have to address them using our strategy for case 2. We'll pick up at that point. Wait, I just can't let you go. So what I want to talk to you about next time is having proper and strictly proper transform expressions. What? So strictly proper is when the numerator is strictly less in order than the denominator. And we'll pick up at that point next time.